Welcome to today's lesson. Shine, can you please pray for us?
Let us pray. Our Father art in heaven, may please bless the day that we have had, and our Father art in heaven, may please be with us during the day. We thank you for being with us until this time, as we're going to be learning about physics, and that you may be with us, help us, guide us, protect us. Pray that we may learn lessons from this class, and that you may be with us. In Jesus' name, I pray. Amen.
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 Today's topic is physics, the quest to understand nature. Our speaker today is Dr. Nkululeki Nokwara. Over to you.
Thank you very much. Did you say Renee? Is that your name?
Yes.
Okay, thank you very much, Renee. Hello, everyone.
Hello.
Share my screen. Come on. Okay, good. Do you have a full screen on your side?
Yes.
Okay, great.
Yes.
So, as introduced by Renee, so I'm going to be discussing physics with you guys. And the version that I've decided to take is to discuss the quest to understand nature. My teaching assistants are disturbing me. I'll call them later. Okay. So I want to discuss physics as a quest to understand nature, because ideally that's what it really is. So you guys already know something about. Is that right? Sorry, maybe I have to close these windows so that we have less noise from, okay, from passerbys. Okay, can you guys hear me?
Yes.
Okay.
I can.
All right. So I need you to answer.
I can.
All right, good. I need you to answer the question. You know something about science?
Sorry.
Do you know anything about science?
About what?
Science.
Science.
Yes,
No,
about no,
not that much.
not that much.
Yes.
That much. We know. No.
Yeah, not that much.
Okay, all right. So then in that case, let's the way I have what is it? So then in that case, let's start the way I have prepared. So I'll give you a biblical basis for why I do what I do. Okay, but in general, some people do physics without a biblical basis, but I believe everyone does it because of the biblical basis, even though they are ignorant of it. Then we'll get into nature, so you can see the problems that we need to understand in nature, and from there we'll get into I'll tell you how we formulate the problem, and then so from what you observe to how to formulate the problem, so we understand something when we can formulate it in a particular way, so that we can predict. Hello?
Oh, yeah.
Am I speaking too fast? Too faintly? Let me know. Am I audible enough? Clear?
Yes.
Okay, all right.
Your voice is a bit low.
My voice is a bit low. Okay, so let me try shout a little bit. Is this better?
Yes.
Okay, good. So I'm going to give a biblical basis for why studied physics, why Newton studied physics, and lots of other big physicists. Although some people do study physics without a biblical basis. But I think we all do physics because of the biblical basis. Then I'll tap into nature. So you can see why we need to understand nature in a particular way. And then I'll tell you how to formulate what we find in nature. I'll just give you a little glimpse into that. And then from there, I will talk about possible careers and what we then we need to think about. So, if you open your Bible to Genesis chapter 1, verses 26 and 28, you don't need to open it. I have it on the screen here. So we read that in Genesis chapter 1. Okay, so tell me, what does Genesis chapter 1 tell us in the Bible? What is it a story of?
It talks about the creation.
It talks about creation. Okay, good. So
Hello?
in chapter 1, verses 26 to 28, it's on day 5 of creation. And God says,
Hello.
let us make man in our image. Is that correct?
Yes.
So God made man in his own image. Then he blessed man. So who's man? It's you and me. Is that right? All human beings were created by God.
True.
So we're all created in Adam on the 5th day of creation. So he blessed us, and then he said we should be fruitful. Is that right? We should multiply, and we should subdue it. So in other words, God gave us dominion over everything in this world, in this earth. Okay.
Hello.
Okay. So he gave us dominion over everything before creation. Before we sinned, right in the creation week. So we came into existence to have dominion. We came into existence to understand nature and to subdue it. Okay. So the goal to understand nature, to study nature, is a goal that we were given when we were created, right at the beginning, before sin came into existence. Okay. So in Exodus, so there are two types of laws that were written by God. One is the 10 commandments. So you know something about the 10 commandments, is that right?
Yes.
Okay. Dr. Bob, is it better if I just speak without waiting for responses? And
Yeah,
then take...
because they are muted
Oh,
most of
okay.
the times. Yeah.
All right. Okay.
And we can hear you. If they don't hear you, they will say.
All right. All right. Then maybe I should also mention that if I say anything that they don't understand, then they are free to ask questions. They can just stop me and ask the question for clarity. All right. So we were given two types of laws. Okay. So God wrote down two types of laws. The one law is the spiritual law, which we find on the 2 tables of stone in the Decalogue. So on the 1 table of stone, we have the first 4 commandments, which relates God to man, or man to God rather. And then the other 6 commandments on the other table of stone relate man to man. So these commandments were...
Yes.
Okay. So these commandments were given to us. They were given to us through Moses at Mount Sinai by God. Okay. So when the children of Israel were leaving Egypt when they were being redeemed into Canaan, they passed through Sinai, and on that mountain, Moses met God, and God gave him the 2 tables of stone. But when he came back down, he found the children of Israel in apostasy, so he dropped the laws and then the tables of stone, and then they broke. And asked him to make 2 tables of stone that were blank. And then on those 2 blank tables of stone, God's hand was seen visibly writing on the 2 tables of stone with his own finger. Okay? So God wrote on the 2 tables of stone the 10 commandments. So God wrote on the 2 tables of stone the 10 commandments with his own finger. Is that okay? So that's the one law, one type of law that God wrote. So God wrote the 2 tables of stone with with his own finger. Now, one of our greatest Bible scholars, by the name of Ellen White, who happens to be in the top 2 most translated female writers, says the following. So in addition to the spiritual law that we're given, to the 10 commandments, God also wrote, God also wrote down what we call the physical laws with his own finger, okay? So he is the one who told the nerves how to behave, how he told the muscles that if you contract, then the arm comes back. If you stretch, then the arm extends. And he told the brain muscles how to work. He told stones how to behave. He told the chair to support you when you sit. Okay, so God wrote down not only the moral law, but he also wrote down the physical law. Okay, so in physics, we are interested to find out what is that law that God wrote in nature, and we want to understand that law. So we understand nature. So we only say we have understood nature when we understand the law that God has written in nature. Okay. All right. So at this stage, let's delve into nature and discuss a few things that we understand and a few things that we do not understand. So let me see if I can quickly find. Okay, I'm just gonna put that slide on. So the slide that you are seeing, the picture of the of what we call a molecule. So it's a tiny thing which is in your eye, at the back of your eye, inside your eye, right at the back. So when for you to see, light has to come into your eyes, and then it's focused at the back of the eye, and then this molecule senses that light, and then it kicks. So it's bent around, so you can see it's bent somewhere. So where it's bent, when light comes in, it stretches like that, so it kicks. And then when it kicks, it sends a signal to the brain through the optical nerve. Okay? So that's how we see. So that's how you are seeing your computer and your phones and everything else there. Now, so that's the one thing that we see, and we understand that through nature. So in order to describe this, we need to write down the law that is obeyed by this molecule. But then, so you notice that this molecule is going to stretch in a particular way, and then bend when there's no light, stretch when there's light, bend when there's no light, and so forth. Now, that it appears to obey quite a number of laws. Okay, so let's park that idea. You have been to the beach, or you have seen the beach on your TV screens or on the internet, and you have seen waterways doing their thing, and they're so beautiful. You have poured out water from a cup, and your juice from your cup, and it behaves in a particular way. And there are particular laws that actually that they're actually that they're actually obeying. You also look into the night sky. You guys are unfortunate to be in places where there is too much light, but when you go out to places, or when there is a blackout, good. So ESCOM is coming in handy. So when there's a blackout, go out of your house or / apartment and look into the night sky and see the stars. So when you look at those stars, so some of those stars are big stars which are bigger than the sun. Some of them are small. Some of them are planets. Some of them are moons. Some of them, there are all sorts of different stars out there. So there are different objects in space, and so there's a whole field of physics that studies all those objects. So when you look into the night sky, so you won't be able to tell immediately, but those stars are organized in a particular way. So some of the stars are organized such that there's a star in the middle. So our sun in our solar system, this sun that you're seeing out there is actually a star. So you have a star in the middle, and then you have different planets going around in different orbits around the sun. So we are Earth, my very earnest. So we are Earth, so we are the third planet from the sun. So the first one is Mercury. The second one is, so my very earnest is Venus. And the third one is Earth. So we are planet number 3 from the sun, from our sun, okay, which is our star. This is our closest star. So when we go from that, did I say that's our closest star? In the true sense of a star, okay? I'll leave it like that, right? So we go around the sun in an oval shape, okay? And it takes us 1 year to go around the sun once, right? Yes? Is that a question? Or is it someone speaking in the background? Okay. So, so there are 9 planets that we know of going around our star, okay, going around the sun. There are 9 of them, 8 or 9, depending on how you count. So there are 8 or 9 planets that are going around the sun. And these planets follow a particular route. They don't deviate from that, okay? So they follow the same route. Otherwise, if they go too close, we die. And if they pull away, we still die from the cold. We go too close to the sun, we die from the heat. Away from the sun, we die from the cold. The temperature has to be exactly optimal. So, so there is a law that these planets follow as they go around the sun, and it's actually a law of gravity. Okay, so we need to understand that law, and at the moment we think we understand it, but there are other factors that we do not understand. Okay, so that's something else that we also need to understand. So I was saying the planets seem to be grouped, or rather the stars seem to be grouped as, so there's a sun, there's a star, and then there are some planets around that. And then there's a whole cluster of stars that you bring together with different solar systems. So what I'm calling a solar system is a system where you have a sun or a star with some planets going around it. Okay, so that's a solar system. So there are many solar systems because there are many suns in the universe. And then these stars get grouped together, and then you get what you call a galaxy. So there are many galaxies in the universe, and So there are many galaxies in the universe, and we are in the Milky Way galaxy, and some of the galaxies look different. So there are people who actually study all of this. It's actually a branch of physics. So, and what we try to understand are the laws that govern the motion of these stars. So let me throw in something. So I said the planets move around the stars, like the planets move around the sun because of what we call gravity. But the planets, but the galaxies themselves seem to be moving away from each other. So in other words, the universe is expanding. So everything is what is called a universe. And in this universe, you have these clusters that we are calling galaxies. And in each of these galaxies, you have solar systems. And then we are in a particular solar system, okay? So the galaxies seem to be moving away from each other at a non-constant speed, okay? And so there seems to be something that's causing, that we do not understand, that is causing all of this. And we call that dark matter and dark energy. We don't call it dark because it's dark, because it's black. We call it dark because it's dark in our minds. We don't understand it. Okay, so it doesn't be. It seems it doesn't behave or like what we expect. It doesn't follow the laws of gravity and so forth. So there seems to be something else at play. Light is a very interesting one. So you are able to, if you're on Wi-Fi, the Wi-Fi signal that you're using is actually the same as light from the sun or light from the bulb, except it has different frequencies. Is that a question?
I didn't do anything.
Okay, all right, that's all right. So, so light from the sun, light from a bulb, screen, light from a flash, and the signal for your cell phone, the signal for the satellite, for your DSTV, the signal for the TV antenna, the signal for Wi-Fi. All of those are exactly the same, okay? So come on. So all of those are exactly the same, even though they behave differently. So I've introduced something new here. So what we do is, in physics, we try to understand, to find out what are the laws that are being followed by nature. And then when we find those different laws, we try to find out whether there is an underlying law besides what we are seeing, okay? So the law that allows the planets to go around the sun, okay, is the same law that allows, I'm not sure that this is clear, okay? So it's the same law that allows me to drop a pen to the table, okay? So when I hold up a pen and I let it go, and when a planet is going around the sun, the two are governed by exactly the same law, by exactly the same force, and that force is called gravity. So we try to find out, we try to reduce everything and see if we can explain everything in a very simple way. So that's the goal of physics. So we were not just trying to observe nature, we observe nature, try to formulate a law, and when we find that law, we want that law to be very simple. At times it's not, but the goal is to find out whether that law is very simple, and we unify and find the most fundamental of those laws, because everything else seems to obey exactly the same law. So let me explain it this way. There are 10 commandments, right, in the Bible, but out of those 10 commandments, Jesus says there are two. The two commandments are, one, love the Lord your God with all your heart. So it's just love with all your mind and so forth. So just loving God. The second commandment is love your neighbor as yourself. So that's the second commandment. And then he continues to say all other laws hang on these two. So in other words, when we look at the commandments, there are 10 of them, and then you can further expand them to 600 and something laws. That's still fine. But the basis of these two, of the basis of all these commandments is just two laws, two commandments. One is love for God, and the other is love for men. So love for God, love for men, that's all you need, and everything else makes sense. So that's exactly how we work in physics. We are trying to find out what are the fundamental laws that nature follows, and then from that, we'll be able to predict and engineer how nature behaves, okay? So by engineer, what I mean is then we'll be able to make new gadgets that behave in a particular way, all right? So,
Yes.
yes.
No, continue. Sorry. I was replying.
Okay, all right. So when you construct bridges, you need to understand what are the laws that govern nature and so forth, right? So as an example, I might ask you to do this, but with caution. If I hit a wall, okay? If I hit the wall, I feel pain. Is that okay? So if you hit the wall as well, sure, I feel pain, okay? So why do I feel pain when I am the one hitting the wall? It's because the wall is hitting me back, okay? So for every action, this is how we formulate the law. That this was formulated by Isaac Newton. For every action, there is an equal but opposite reaction. Don't worry about the words. The basic story is if you push something, it pushes you back. Okay? So if you hit a wall, it hits you back. So that's just one law. And we use that a lot in the construction of to keep cars down when they are speeding, to construct buildings, to make chairs. So you don't know all this, but this is what you are doing. When you sit on a chair, you are pushing the chair into the ground, but you're not sinking into the ground because the chair is pushing you back or the ground is pushing you back up to balance the force that you are pushing down, okay? So when you do that, so we try to understand those laws, and it comes out, well, it's just one law. For every action, there is an equal but opposite reaction. You hit the wall, it hits you back. Okay, so I've highlighted a few examples from nature. Why are plants green? Okay, so let me pick that example. Why are plants green? So plants are green. So plants are green because the molecules that make up, the molecules that you find in the plants, which are responsible for the manufacturing of food in the plants, the molecules are called chlorophyll, okay? So the chlorophyll molecules absorb light and then emit light, okay? So the light that is the color that you find, so that color is green. So white light, for example, light from the sun is white. So white light consists of all the colors of light together, okay? But then materials absorb this light and then emit some of the colors. So for example, this is a green pen. So I'm saying it's green because I have white light coming in, and then so I have white light coming in, and then the molecules in this pen are absorbing all of that light but emitting the green light. So only the green is coming out, so this is green. Here only the red is coming out, so this is red, okay? Okay, let's see if I can find something. All right, so this is black. That means there's no light being emitted at all. So this is absorbing nearly all the light, okay? So that's why it's black. So it absorbs all the white light. So those are all interesting examples of systems in nature that we need to understand. So we already understand some of them, but we do not understand a lot of them, okay? So by understand, I had mentioned that by understand, we only say that we have understood something if we can write down an equation for it, okay? So the language of physics is mathematics, okay? So we only say we have understood something in physics if we can write down a mathematical equation for it, and then we are able to solve that equation to predict how this particular system will behave. So for example, when the Earth is going around the sun, we have an equation or a couple of equations that we can write down for that. And then from those equations, we are able to solve those equations and predict where the Earth will be at a particular time, and then predict what it will do and things like that. So that we understand, but we are unable to predict some materials behave like metals when they are not. So a metal is like a wire. Okay, good. So this here is a metal. Okay, this is a pencil. This is a mathematical set. Okay, just the case. So this is a metal. But if you look at a tile or if you look at the wall, that is not a metal. So there are some tiles that behave like metals when they are cooled down. So you pour liquid nitrogen on them to cool them down, and then they start behaving like metals. So we don't know why they behave like that. So there are lots of these materials that behave like, we don't understand why they behave the way they do. There are also other materials that behave like both metals and non-metals, like the insulators. So what happens is, so you'd have a metal inside, so you have one material. So on the surface, it behaves like a metal, but inside it behaves like a non-metal. So there are such materials. We understand them in part, but we don't understand them fully. So there's a lot that we understand in physics, and there's a lot that we do not understand in physics. So if you were to become a physicist, you would have, your duty would be to continue to add to human knowledge and understanding. So you want to help people understand nature. That's your basic goal, and then the engineers can take it up, and you make new products from that. So the way it works is that we have to write down mathematical equations to describe nature. So as an example, I had this molecule here, which is responsible for vision in your eye and other mammals. And these are the electrons and so forth. So you'd want to understand how that works. So to understand how that works, you write down this equation, which looks complicated, but to a physicist, it looks simple, okay? So this is a simple equation that you would write down. I won't try to explain what it says, but because you need a bit more training to do that. So you write down this equation, and then you try to solve this equation. So this equation is actually too complicated to solve on a piece of paper. You can't solve it on a piece of paper for a molecule such as this, okay? So if you want to understand this molecule, you write down that equation. So that equation labeled 5, and then you put in the parameters, and then you try to solve the equation. So you can do that for that molecule, and then it will tell you how that molecule will behave. And then you can throw maybe green light at that molecule, and then you see how it's going to behave. You can put the molecule in a microwave by just adding a term mathematically to see how the equation, to see how the molecule will behave in a microwave. So these are all these interesting things that you can do. So so basically you are modeling. So, and then you are trying to solve this equation, and then you realize you can't solve the equation directly. So you need a computer. So you get a huge. So you get a computer, and you use that. So you get a computer, and you try to use that computer to solve that equation. And then, so you start off with a small computer, and then you realize the computer is too small. It's not powerful enough. So you need bigger computers. So you end up with a branch of physics where people actually just use these computers to solve these complicated equations in order to see whether we describing nature correctly. And that branch of physics that uses computers to solve these equations is known as computational physics. So we basically have an experiment, right, to see how nature behaves. So you observe, when I open my eyes, I can see mom and dad, okay, or I can see a pen and things like that. But why do I see them only when there is light, and when it's dark, I can't see them? Or I see them because the light has to shine on their face and then bounce off from their face, so their face reflects the light into my eyes, and then in my eyes the light is absorbed and it's focused at the back, and then or the back of the eye, and then at that back of the eye, there's a molecule that actually senses the light, and then you try to understand that molecule, and then to understand that molecule you need an equation, so you write down that equation, and then you try to solve the equation. It's complicated, so you need a computer, so you solve the equation on a computer. So what have I just said now? I've said there is experimental physics. So in experimental physics, you observe and you do experiments in the lab, and then you also test whether the predictions are correct of the theory. And then there is mathematical physics, where you write down the mathematical equation to describe nature, okay, what you've observed. So you write down an equation for that to describe nature. And then there's so that's called mathematical physics. And then there's computational physics, where you try to solve the equations on the computer, okay, because it's a lot of work to solve the equations. So those are the three main branches of physics. But then for each of those branches, there are people who are working with galaxies, trying to observe the galaxies and understand what's happening, and that's called cosmology. For each of them, there are also people who work with materials, who observe that the wall doesn't behave, or the pencil here, it's wooden, so it doesn't behave like a metal, right? Electricity can pass through the metal, but it won't pass through the wood. But even though it won't pass through this wood, it can pass through the lead of the pencil. Okay, so so there are people who work on materials and actually try to understand that. There are people who also try to, who work on who break down matter, who work on the nucleus, and they try to understand the particles making up matter. So that again is a big job. So there are big accelerators, big this and that being done, and that have been built. And yeah, we are discovering new things every day. So it's just a beautiful field of work. So I've mentioned nuclear physics, I've mentioned condensed matter physics, I've mentioned cosmology. Computational physics is almost in all of those. And yeah, there are other branches, but those are some of the main branches of physics. So what would you do if you became a physicist? So you could be an experimental physicist, right? Like Dr. Pepile Ngube here, she's a friend of mine, studied at the University of Witwatersrand, okay? And come on. So, okay, so she studied at the University of Witwatersrand, and so she holds a PhD in experimental physics. She specializes in nanomaterials, and she's designing new materials, or rather new components for electronics in the nanomaterial regime. So if I said something that you don't understand, you should ask. Okay, I've told you she does nanophysics. So she only does experiments. She doesn't do the theories. She doesn't write down the mathematical equations. She only does the experiments. So she was in a lab here in which she was doing a PhD, and it's a very fancy lab with very interesting equipment that she works with, and it's just a beautiful place to be in, right? So you can be an experimental physicist to do experiments. Then you can be a mathematical physicist to write down equations like this and solve them. Then you can be a computational physicist to take these equations and put them in a computer like that and then solve them. I took these images from the internet. So this is some supercomputer. So a supercomputer doesn't look like your laptop or the desktop at home. It's a big frame with multiple computers joined together, working hand in hand to solve big problems that you can solve on a small computer. So this is a supercomputer. So most of computational physics is actually done on these supercomputers. You can also work in finance. I picked this up from a paper in on the internet, but you can also work on finance as a physicist. So you use your skills to model materials and then and apply that to financial systems. So what you do is you take, I'm looking for a quick example. Okay, good. So let me just stop sharing here so that you can see more clearly what I'm trying to do. So suppose these atoms or electrons in a material. Okay, so suppose these atoms or electrons in a material. So these guys have a particular spin. Okay, so they spin either clockwise or anti-clockwise. And then I have many of them in a magnet. So you guys have played with magnets or not. So in a magnet, I'll have many of these guys, and they will be aligned. They are either all pointing up or all pointing down, okay? So I can use the example of a magnet to describe what happens in a financial market and try to predict how the financial market will be. Yes?
Guys,
Okay.
I'm in a Zoom meeting.
Okay. Okay. Sorry, I'd been muted. Yeah. So we use this. Sorry. Okay. So we use this to try and predict what will happen when COVID-19 hits. So we know that there will be lockdown and things like that. But what will happen to the price of gold? What will happen to the price of petrol? Okay. So you can model all of that by studying different systems from physics, and then imagining them to be financial instruments. So if I'm thinking of a magnet, magnetic system, then if I have COVID, then maybe this will turn, so if this was pointed up, then there's COVID, this will point down, and then I can check how far this will go. Okay, so maybe for the rest of the year, where the markets will be closed or they'll be performing poorly. Then these are things you can compute using physics. In principle, these are things you can compute using physics and try to make sense of. So basically, that's what physics does. So you can be an experimental physicist doing experiments. You can be a mathematical physicist writing down equations. You can be to describe nature. You can be a computational physicist using a computer to understand nature, to solve the equations to understand nature. And you can work in engineering. You can be an applied physicist and so on. So you can work in engineering to bring new products into nature. I mean, into life. For example, when Apple designs a new cell phone. So I think they'll be announcing their new iPhone soon. So they'll probably use a new screen or a new screen technology. So to design new screen technology, material from nature and alter, understand how they work, and then use them to make a phone screen. So to do that, you need a physicist. That's what a physicist does. Then you can also be finance, modeling how the financial world works. Okay, so that's about everything I wanted. No, not everything. That should be about enough of what I wanted to tell you about physics. I had a few experiments or demonstrations that I wanted to perform, but they don't seem to fit well in the final line of thought. So I hope you picked up something. All right. Oh, so the last thing was, what do you need? Sorry, I forgot that part. So what do you need to be a physicist? Okay, come on. So what do you need to be a physicist? So you need to be inquisitive. So in other words, you need to ask, why does nature behave the way it behaves? You need to observe and ask, why is it doing this? Why is it not doing that? Okay, why is the pen falling down? Why is it not falling up? Okay, those are the questions you should be asking. Those are the questions that a physicist answers. Then in order to answer those questions, you need to work hard, but hard work alone is not sufficient. So you also need to be disciplined. So work like washing dishes is very important. Work like wiping the floor, cleaning up, that's very important if you're going to be a physicist. You cannot be lazy and be a physicist. So your mind seems to work well when your hands also work a lot. Okay, then you need to study mathematics because that's the language of physics. Then you need to study physical sciences in school, and then afterwards you need to study physics until you get a doctorate, until you finish school. So school will finish at doctoral level. And then you can also study other things like computing, like geography and so forth. That will help you pick up a lot of other information that you will need later. All right, so that's that about physics. So, and I hope it made sense. Let's see if you guys have any questions. So there's some, I'm seeing charts, but I can't. Okay. I thought I was seeing charts. Okay.
All right.
Okay.
Thank you, Doctor, for the presentation. Now I will open the floor for questions. Please raise up your hand if you want to ask a question.
Did you guys understand everything that I said?
I don't see any hands. Oh
Okay.
yeah, Tine, you can speak.
My question is, can you be two? Can you do two jobs, but being a physicist?
Okay, can you be two?
Can you be a mathematical physicist and a computer physics as well?
You can absolutely, but the work that you would have to do is a lot. There are people who do that, but you end up with a lot of work. And the way it would work better for you is if you then recruit other physicists who specialize in different subsets, and then they can work on the different things while you supervise from above. Then that way you can work on more fields than one. But it's a lot of work. It can be done.
All right. I don't see any other hands.
Okay, there's a question that was found. Oh, are there any
Are there other jobs, but are there other jobs than being physics?
Yes. So I've mentioned finance. I've mentioned applied physics and engineering. So physics is the base of a lot of of a lot of other professions. So there are people. Okay. So engineering, there would be no engineering if there was no physics. Okay. I'm quickly trying to think of other. So you can also be a programmer. You can just work in computer science because you have very good computational skills. So you can just work in computer science as a programmer or some software developer there. Yeah, and then you can work anywhere else where. So you can work anywhere else where a well-trained mind is required. So because you are trained to understand nature in physics, then you can work anywhere where there's a complicated problem that people don't understand, and you try to solve it. So as an example, a physicist would do a very good job with atom and fluid. Uh, that's it's a complicated problem. A physicist can turn around a whole economy like Zimbabwe. So that whole economy can be turned around if you put a few physicists together and ask them to solve the problem. So whenever you have a complicated problem, even if it's not physics, you just ask the physicists, set them loose in there. They should be able to do something about it. What about IT specialists? Yes, you can do IT after you do your physics degree.
I've noticed that some people from engineering are actually finance officers or CFOs who end up being chief executive officers. How do you explain that?
From the physics perspective, so it's okay. So there are two routes to it. One is people have a first degree in, say, engineering or physics or something like that, and then thereafter they get a second degree in another field. So you can get particularly, say, a master's in business administration that you can do from any field. So any first degree will do. So you can do that. But I think the biggest advantage of having a physics training is that you are trained to solve complicated problems. And so you would do well even in the field of business where you might encounter complicated problems, and then you should be able to solve that.
So if you bring it to a church setup, for instance, in terms of witnessing, in terms of evangelism and all that, Would we be better off, say, having physicists or having scientists working at the conference, planning and strategizing? Will the church grow that way?
It should grow in leaps and bounds. It's actually interesting that the training of pastors at Solusi includes science. So physics so they do a bit of physics in there as well. So physics just makes you jacked up. So you kind of you kind of see, when you understand nature, you appreciate God more. So and also if you wanted to witness to academics or other scientists and so forth, you need people who have who understand those people as well, you see. So that's why Jesus, in general, that's why God did not send angels to preach to us. Instead, he sent us to preach to one another, because we understand one another. Angels don't understand us. So scientists would understand other scientists. So and the gospel is supposed to go to all people. There are also interesting. There are also a very interesting phenomena from the world of science, from nature in general, which we don't understand. So, for example, Jesus turns water into wine. So, without a physics training, you'd be like, oh, well, it's just a miracle. Water became wine. With my physics mind, I'm thinking, what are the molecules that make up water? What are the molecules that make up wine? How much of the water was there? How much of the wine did he end up with? What is the mass of the water that he started off with, and what is the mass of the wine that he ended up with? So how did he convert this to that? And then you start realizing the miracle is much bigger than what we originally anticipate. So what I'm trying to say is, understanding nature makes you wonder more about God and his plan of salvation.
Hi, Doc. I also have a question.
Yes.
Can you hear me?
Yes, I can.
Yeah, Doc, when we look at, I'm talking to my daughter Isabella here. When we look at the biblical aspect, actually what happened was the earth was created by God some thousands of years back. But from physics, there are millions of years that are involved in these processes, and these things might have started on their own, you know, with some explanations that we don't understand. Biblically, there was let there be light, the creation of the sun, the moon, the stars, the planet, division of water, which is straightforward. But I'm talking to my daughter here in terms of physics. We hear all sorts of theories. The sun started like this, the earth started like this, millions or billions of years ago, and stuff like that. How do we reconcile those as Christians who want to also be physicists?
Okay, thank you for that question. So let me do the following. I have 3 pens here. So I have blue, green, and red. Okay. Each of these pens have ink. Okay, and it's just ink. The only difference between these pens is
I can hear, but
sorry. Okay, so the only difference between these pens is the ink that's I'm going to that's going to come out right from them. Okay, so if I use the blue pen, okay, if I use the blue pen, this is what I would write. Okay, so that's the blue pen. If I use the green one, this is what I would write. And I'm writing on the same piece of paper. And if I use the red pen, this is what I would write. Okay. Now, the fundamental problem that people make, or rather the fundamental error that people, and this is actually how we move from in leaps and bounds from and expand our knowledge in physics. So the problem is that people assume that because these are pens and they all have ink, they'll write exactly the same. But what I have just done is demonstrate that the blue will write blue, the green will write green, and the red will write red. So in other words, the laws that govern the different pens are actually different. The red one reflects red light, the green one reflects green light, the blue one reflects blue light. So they're reflecting different wavelengths of light, right? Even though initially they are all pens by the same manufacturer and so forth. So what am I trying to say? The laws that we have, the laws that we discover in nature, we do not always fully understand. So what we do is, I could study, okay, good. I could study the planets going around the sun, and I would use the laws that were, the equations that were written by Isaac Newton. So Isaac Newton wrote these laws in the 17th century, I think. So, but these laws, even though they describe all the other planets, there's something that they don't describe about Mercury. Okay, so there's something that they don't describe about Mercury. So in order to understand this thing that these laws do not describe about Mercury, we need a new theory. Okay, and this new theory is a theory called general relativity. Let me just elongate this explanation a little and use my teaching assistant. Just hold on for me. Teaching assistant. Yeah, there. Yeah. So I've just called in a couple of my teaching assistants, and I want to use okay, I'll use this, but I need something heavy as well. I'm going to use these two things. Okay. All right. So this is my brother here, and he's going to be my teaching assistant. So the law that allows us to describe how nature, how the planets go around the sun, is the law of gravity. So it basically says if I drop something, it falls. So in other words, the planets are continuously falling towards the sun. Okay, so that's what it says. But those laws don't allow us to describe Mercury fully. Okay, so if I want to describe Mercury fully, I need a new law which was written by Einstein to describe gravity again. So that law is the following. So this is my teaching assistant. Let's hold that. Okay, let's hold this flat. Okay, let's hold it there. Let me see. Okay, let's stretch it. Okay, so this is a fabric, and in physics we think of space and time as a fabric, okay, like that. So what we do with that fabric is when there is no matter, there is no, the fabric is flat. And then when there is matter, let's stretch. Okay. So when there is matter, so I'm going to put, this is my matter, so this is the sun. So when there is matter, this is what happens to it, right? So in other words, if this was a planet and there is no sun, and I throw the planet on this fabric, it would move straight. Okay, there's nothing to change its rotation. But then if there is matter, if I put matter, so I put the sun in. Okay, my teaching assistant needs to eat. Okay, right. So when there is matter, please stretch. Yeah. Okay. So when there is matter, this is the sun. I'm putting that sun in. So my fabric has now curved. Okay, it is bulged. So when I throw in the planet, it no longer moves straight. It now moves. The word straight is now a curve. It now moves in a curve. Okay. And that's the new theory that I need to describe. Thank you, teaching assistant. So that's the care. I mean, that's the new theory that I need to describe how these planets work. And when I do that, then I find Mercury. So what have I just said? I've just said that the laws that we discover are not applicable universally. So when you try to apply them universally, they break down. Okay. So we tried Einstein's description of gravity. It describes all the other planets, but not Mercury. And then we need, Newton's description of gravity it tells us they're just falling. So that works for all planets, but not Mercury. And then we need Einstein's description, which tells us about the fabric of space-time. And then you put the sun, and then it bulges that fabric and so forth. And then the planets follow the curves inside the curved or bulged fabric. But then that theory again doesn't work when I think of atoms. So it's not powerful. That theory, it just breaks down when I think of electrons in matter and so on. So all theories basically have their limits. But what people try to do is try to apply these theories beyond their limits and see if it works or breaks down until we discover something new. So this is exactly what you have with the story of creation. So when they tell you that the universe is 13.4 billion years old, that is based on a particular theory, and but that theory we know is not universal. It's very successful in describing a lot of the physics, but it doesn't describe all of physics. So that's the complication. Now maybe I should throw in a comment quickly and say, when you study science, particularly physics, there is one mistake many people make, and it is the following. It is to believe that when they study science, they're going to discover God. It's not true. When you study science, they're going to discover science. So when our faith is not wrong based on so how do I put it? So the story of creation is not wrong based on the theories that have been published. So those theories are not necessarily correct. So that's the long and short of it.
Thank you. It's well understood. Much appreciated.
Thank you very much. There is a question here that says, do physicists work in groups or individuals? Do physicists work in groups or individuals? They do both. So in the past, they used to work in as individuals, but now the physics has become so complicated, many people decide to work in groups. So collaborations are the order of the day. But you can still work as an individual. There's nothing wrong with that. Although the problem becomes very complicated. Okay. Renee?
I don't see any more questions. So thank you, Doctor. I will ask Mimi to pray for us.
God, please bless us. Thank you for this beautiful evening. Thank you for teaching us so many things. We've learned so much over the past few minutes. Thank you for giving us access to knowledge and food and water. Amen.
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 All right.
Amen.
Thank you, everybody, for